Better, yeah, because this is the microphone for the string. So. No. Hello. Very loud, actually. So, hey everybody. Is this working? Really, right? A little bit. Yeah. Okay.
Only goes back 5 years.
Not really loud, right? Okay. Okay. Much better. All right. So, welcome everybody. I would like to ask the people on the food side to have a sit, grab some food, and stay comfortable. So also welcome to the people joining us via YouTube. Today you will only see like the slides and not the people in the room because it's more easier, because we're going to see some code as well. So it's easier. So let me introduce myself shortly. I'm Niklas, working for Just Quantum. And today we're going to have two guests from IBM, Chris Wood, who's talking about Qiskit and the IBM framework, doing a little deep dive in how to simulate quantum algorithms using Qiskit Air. And our advisor, Fate, will going to show what else is possible doing quantum simulation and pointing out some nice applications. So, Chris, the stage is yours.
Great. Thank you. Okay. So my name is Chris. I'm a research scientist at the Quantum Computing Research Group at the IBM T.J. Watson Center in Yorktown, New York, USA. So I've been studying quantum computing for around 10 or so years. I studied physics and mathematics in undergrad, and then did a PhD in studying noise in quantum devices, quantum physics, quantum systems, and then have been working at IBM developing our software library Qiskit, and also still studying noise in quantum systems. So I'm going to give you a little bit of an overview of what we mean when we talk about noise in a quantum device, how we model that mathematically, and how we can include that in simulations to try and understand. We're actually trying to look at quantum algorithms run on near-term devices, how those errors and noise might affect the results of those algorithms. So that's a quick outline of all the things I'll try and get through in half an hour. how we model and simulate ideal quantum systems without errors, then how we model and simulate noisy quantum systems with errors, the software tools we've been developing at IBM to use to study quantum computing and execute quantum computing, and then a quick demonstration of some of our code that you can see in Jupyter Notebooks online on our GitHub page. So to get started, I'll start with the way we consider an ideal quantum system. So an ideal quantum system is some system described by quantum mechanics in perfect isolation. It doesn't interact with anything else. And so this might be something like a single spin or a single photon or an atom. And from quantum mechanics, we have a very good mathematical model for how to describe these systems. So assuming you've all heard of qubits and are familiar with the block sphere, so basically for a general quantum system, we can represent the state of that system by a complex vector called a state vector. And for the case of a single qubit, a two-level system, that looks like a vector that points to somewhere on the surface of the block sphere. So this can be anywhere on the surface of this block sphere as a representation of an ideal quantum state. And then if we want to describe how this state can evolve through a computation or evolution, we use what's called a unitary matrix. So why a unitary matrix? Unitary matrices are exactly the set of matrices that preserve the length of a vector. So if a state is a normalized vector, this means that after applying the matrix, it will still be a valid quantum state. And in terms of a block sphere, a unitary is some operation that will map that vector to some other vector on the surface of this sphere. And if we actually care about the dynamics of this evolution, not just a discrete gate model, then the dynamics of a quantum system, an ideal quantum system, is described by Schrödinger's equation. So this is a different ordinary differential equation describing the continuous time evolution of a state vector. And the solution of that differential equation is exactly a unitary matrix. So here's a picture showing how we might consider a rotation of the block sphere of 90 degrees as incremental steps as it goes through time. And then finally, the last piece of describing a quantum system is measurement. So for an ideal system, measurement essentially collapses the state vector. So if I had this state that was a plus state, so it's some superposition of 0 and 1 on the block sphere, and I measure it in the z basis, the outcome of that measurement is always 0 or 1. And depending on which outcome I get, the state vector collapses to the outcome I observed. So with probability 1/2, I might have got the 0 state, and then that would be my new description, or probability 1 is below. So we talk about how we actually simulate a quantum system now. Then the reason that we care about quantum computing is that it solves certain problems that you can't simulate classically, that are exponentially costly. And one of those problems is just simulating a quantum system itself. And the reason why simulating a quantum system on a classical computer is inefficient is there's exponentially much information you need to describe it. So if I just take instead of a single qubit, if I consider an n qubit state vector without any approximations, if I want to store that on a classical computer, that requires 2 to the n complex numbers that I have to store in a vector. So the coefficients of this state vector in this expansion. And so to put that in perspective, if I wanted to write down a state vector to store in memory on a computer of a 20 qubit state, that would require about 17 megabytes of memory just to store all those complex numbers. 30 qubits now would require about 17 gigabytes of memory, so that's already hitting kind of the memory limit of a typical desktop. And then if I went up to 40 qubits, I'd need 18 terabytes of memory, so that's into supercomputing cluster territory of the memory requirements just to store the state. And so if I can look at Wikipedia and see what the current top 1 supercomputer in the world is the Oak Ridge National Labs, the Summit machine. So if I wanted to just store a state vector using all the RAM available on that system, I could get up to about 47 qubits, and that would require about 2.2 petabytes of memory just for writing down a state vector. But just writing down a description of a state isn't very interesting on its own. I then need to describe how to evolve it. So as I mentioned, that's done with unitary matrices. So matrices are the square of the size of vectors. So if I wanted to just write down a 10 qubit matrix, now that's about 17 megabytes of memory. 20 qubit one would be about 18 terabytes of memory. So the key here is we want to do a simulation of a state vector on a system. We don't ever write down the full unitary matrix to evolve the state vector by, except for a very small number of qubits. what you do is you actually evolve the state vector by these smaller matrices that you can write down, and then you iteratively update the state vector. But each update takes time, so you can try and optimize this in various ways. So for example, I could compute a 3-qubit matrix by combining several gates together and then apply that to update the state vector. So this is how a typical state vector simulation would work. Okay, so that's only the story of how we actually simulate a quantum system without noise. So in the real world, our systems are never perfectly isolated from anything else. We want qubits to interact with each other to do multi-qubit simulations. They exist in a laboratory and in an environment. And there's all sorts of effects that break this assumption of an ideal quantum system. So there's thermal effects, there's like lasers and control pulses and microwaves, and maybe there's control errors and interactions with unwanted neighboring systems. So there's a mathematical model for describing these open quantum systems, as we call them, with a rigorous mathematical framework that lets us approximate that. And basically what this does is the system we care about, perhaps our n-qubit chip, we call that now an open quantum system, and we consider the environment, the neighborhood of all the effects that influence the state of that system, but we don't want an explicit description of. And then that joint system of the system plus environment we model mathematically as an ideal quantum system. And then by removing the environment from our model, we can get an effective description on the system alone under some new rules that describes the state and the dynamics of that system. And so this is a very good model for many systems that we're interested in, such as using superconducting qubits or trapped ions or other architectures for real quantum devices that we use in the laboratories. So going back to our block sphere picture for how we describe that. So instead of a state vector for an open quantum system, we use a density matrix. So a density matrix essentially has the same properties of a state vector in that it can reproduce the output statistics of any measurement I would do on the system. But it's a more descriptive description of a state. You can describe states that you can't describe with a state vector, such as classical mixtures. And in a block sphere, what that looks like is now instead of just only being able to describe states on the surface, every point inside the block sphere also corresponds to a valid density matrix and quantum state of an open system. And now if I want to describe evolution, unitary is just one kind of evolution. The most general evolution I can consider is mathematically described by a completely positive trace-preserving map, or CPTP map for short. So without really describing what that is, you can think of it as the most general map that takes a density matrix to another valid density matrix. And it has some special properties to ensure that the output is also a valid quantum state. And these maps you can always write as some sum of matrices, K here, acting on a density matrix that are called Krauss matrices. And if you care about, I guess, so this picture here I drew was a map that, rather than a unitary, what it's doing is it's taking this state and pushing it into the center of the block sphere into basically a completely random state. And to describe dynamics, instead of Schrodinger's equation, you can use what's called the Lindblad equation, which is a generalized differential equation acting on density matrix that also allows for these non-unitary dynamics, or called dissipated dynamics. So an example of a dissipated dynamic would be some evolution that, rather than rotating here, is actually pushing it towards the center of this block sphere. And then measurement, again, there's a slightly more description of measurement, where now the outcome after a measurement doesn't necessarily have to be a state vector. It could also be a density matrix, so there can be some randomness. Even if I observe an outcome of 0 from my measurement, that doesn't guarantee now that I'll still be in the 0 state. There might be some uncertainty still remaining because of noise in that measurement. So how do we include this open quantum systems and noise framework into a simulation of quantum computation? So the simplest way to do this is with what's called a gate-based error model. So if I take a quantum circuit like is shown here on 3 qubits, this circuit would prepare an entangled 3-qubit GHZ state by first putting the first qubit in a superposition and then entangling it with the next 2 qubits with these controlled NOT gates. So the idea of doing a noisy simulation in this model is that we treat every noisy gate as being an ideal unitary gate followed by one of these possibly non-unitary CPTP error maps. So that can look something like this. So the simplest case is I only consider errors that are local to the qubits in a gate. So if I do this Hadamard gate on the first qubit, I can then add some error term that also acts on the first qubit. And then if I do a 2-qubit gate, I can add an error term that acts on the 2 qubits involved in that gate. And this can be a good description for many types of errors you want to model in a quantum circuit. You could also consider more general types of errors, such as non-local error models. And in this case, I might relax the description of having the error only act on the qubits in the gate. So I could consider non-local errors that act on every qubit in my system. So even if I'm only trying to do a gate on a single qubit, doing that gate might actually affect the other qubits in some unwanted way. So this allows you to model these general noise interactions. So now to talk about simulation again. Simulating ideal quantum systems is already exponentially difficult. Simulating open quantum systems is even harder. So if I wanted to write down a density matrix, for example, it's a matrix, so it has the same memory requirements as writing down a unitary matrix. So now to even write down a 20-qubit density matrix, you need several terabytes of memory. And so if I went back to this example of using a supercomputer like the Summit, then using its memory, I could only write down a density matrix of about 23 qubits, and that would already require over a petabyte of memory. And then for considering these CPTB error maps, because they're written, you can write them as a set of matrices, where each matrix has the same memory requirements as the density matrix or unitary, but now there's potentially 4 to the m of them. Now, if I wanted to write a general description of an error on, say, 5 qubits, that's going to take 16 megabytes, and even 10 qubits is now going to take terabytes of memory. And if you try and push that up to 15 qubits, you're talking about exabytes of memory, so that's just completely impossible. So what this means is that, again, when we're doing simulations, like with unitaries, we basically apply these CPTB maps iteratively. But if we're trying to model non-local errors in a system, this kind of sets a maximum size of the non-locality of an error we can consider in a simulation. If I have a 20-qubit device, for example, I can't just assume that I have a 20-qubit error term. I apply every term of an arbitrary sort because I can't write down that 20-qubit error term. Of course, you can make approximations and things to get around this, but this is a general consideration to consider. So I've spent 10 minutes describing how hard it is to simulate a quantum computer with a classical computer. So you might ask, well, why do we want to do this in the first place? And basically that's because we need to be able to do simulations to understand the behavior of the devices we have to improve them. So you might have heard of this acronym NISQ that's been used recently in various literature related to quantum computing. And so what this stands for is noisy intermediate scale quantum computers and quantum devices. So at present we have devices that have of order tens of qubits, and in the next few years we'll be getting up to perhaps hundreds of qubits. So this is what we mean by intermediate scale, and these devices have a lot of errors that mean they behave in this open quantum systems framework we need to model, and we need to be able to model these to understand their properties. So just to put some of IBM's chips into perspective, so in 2016, the cutting edge was a 5-qubit chip. 2017, it was up to 16 qubits. 2018, 20 qubits. So we're still in the regime where we can actually simulate these devices, and we really need to do that to understand their performance. So having good models of the errors in a device lets us design better control sequences and better calibration to improve the performance of the devices for other applications. It's also necessary if we want to estimate the performance of algorithms run on real-time devices. So if you're some company interested in exploring near-term applications, you want to know how well you can expect to run certain quantum algorithms or applications with the given error rates of the device. So you can study those sort of things doing these noisy simulations. And also understanding and having models for the error is also guides hardware and engineering improvements for the next generation of devices. If we can prioritize what kind of errors we think are dominating our devices, then that can give us some fundamental direction for the physics of the devices for improving their performance in the next iteration. So moving along, that's a very quick high-level overview of how we simulate noisy quantum systems in this circuit-based model. So now I'll talk a bit about the software we can use to actually do this. So at IBM, for the last 2 years, we've been developing this open source software stack called QuizKit that basically we use to to run our quantum experiments, either on the devices we make available in the cloud or on simulators. So QuizKit is a collection of Python libraries and applications that allow you to look at algorithms and applications for quantum computers, to actually just design circuits directly. If you have a specific circuit you want to study or design for research or applications, optimize these circuits to be able to run on different configuration of devices based on maybe their coupling or number of qubits, and then actually send this to be run on one of our devices through the cloud or on a either online or local simulator, and get results back and actually play around with quantum computation. So QuizKit, from its first version about 2 years ago to the current day version, has grown a lot and has broken up into sort of 4 elements or components. So overall, the whole software is written in Python, Python 3. It's open source under the Apache 2.0 license. And the 4 pieces of QuizKit. So at the core, there's QuizKit Terra, which is basically the collection of APIs and tools and classes we use to build quantum circuits, compile them, optimize them, and execute them, whether on hardware or a simulator. And then built on top of QuizKit Terra, there's 2 more recent libraries, QuizKit Aqua and QuizKit Ignis, which are a collection of functions and classes that generate sets of circuits to execute, where these circuits allow you to explore specific applications. So for Ignis, it's more designed towards device characterization and error mitigation. So it builds sets of circuits to implement characterization things such as quantum state tomography or randomized benchmarking, which is the tools we use as researchers in the lab to profile the error rates of our devices and study their performance experimentally. Aqua is high-level applications and algorithms. So this contains, for example, sets of library of functions to explore applications like quantum chemistry or machine learning or finance, and the various components used to build these applications on top of QuizKit. And then finally, what I'll talk about for the rest of it is QuizKit Air. So QuizKit Air is our simulator framework. So this is the piece when you make a circuit in Aqua or Ignis and compile it down, and you want to run it on a device. Maybe you also want to run it on a simulator. So this is the simulator framework we have to do noisy simulations to study these processes. So just a very quick overview of what QuizKit Air is. So it's the simulator backend for QuizKit. You can install it locally to run it on your laptop, or run it on a desktop, or run it on a server cluster. It's also the basis of the online IBM simulators, so you can run it through the cloud interface as well. The code's written in C++ for performance and speed, though it's all wrapped through an interface in Python, so you can use it with the rest of QuizKit. And the key point is it includes a lot of highly configurable noise models and functions to help you generate noise and model errors on devices in your simulations. So I'll just go through now. So I just want to mention that, so we have the QuizKit GitHub contains all the source code. You can look at the using the various pieces of QuizKit. But one important directory is this QuizKit tutorials directory, which contains a lot of Jupyter notebooks on how to use QuizKit, from very beginner tutorials that introduce you to the basic concepts of quantum computing, through to advanced tutorials of actually using the pieces to, say, study applications like quantum chemistry or randomized benchmarking, or also several tutorials on how to build custom noise models in the simulator, which are what I'm going to talk through for the last 10 minutes of this talk. If I can. Okay. So if you're interested in this stuff, I would encourage you to go look at these at your own time. I'm only going to give a very, very sort of quick flavor of 2 of these notebooks, just related to what I talked about earlier about noise models. And so the first one I want to go through is this device noise simulation notebook. So this is designed for people that are interested in maybe an application of quantum computing, so running circuits produced, say, from Aqua, and they want to start looking at how it might run in the presence of noise on a device, but they don't know a lot about quantum noise themselves or the framework of it. So this introduces some simplified models you can just automatically generate using tools in QuizKit to run noisy simulations without all this expert knowledge. So basically, if you're not familiar with Qiskit, there's a whole bunch of Python libraries you can import. So the key one here is Air is the simulator provider, so you can import Air. IBMQ is the provider for our online simulators and devices. And the rest is basically classes to build quantum circuits in Qiskit. So the device noise model is basically, the devices IBM makes available online in the cloud, so the 5-qubit, 16-qubit, 20-qubit, store some properties in their description about the kind of average error rates on the device. So you can query that and get this information from the back end. And so what this device noise module does is it can allow you to take one of these back end specifications and generate a simplified noise model for that device automatically that then you can use for simulations. So how you do that is if you need to have an account with the IBM Quantum Experience to be able to use those devices through the API. But if you have an account, you can look at the devices you have available. So for example, here's 3 hardware devices and 1 simulator. And then, so if I pick one of these devices, such as this 16-qubit device, I can then, using the API for the device, get its properties through the cloud. And also something called a coupling map, which gives you a configuration of the allowed gates between qubits. And then I can use that to do a more accurate simulation. So in this example, the test circuit is, again, so that 3-qubit circuit I showed in the slides of preparing a GHZ state. So that's going to prepare this 3-qubit maximally entangled state at the superposition of all qubits either down in the 0 state or in the 1 state. And so using Qiskit, I can build this circuit. If you're not familiar with Qiskit and this process, there's also tutorials on building circuits and using the basic building blocks. So the key point then is once I have this circuit, I can then choose the simulator backend to run on. So this would be running on the local simulator, for example, on your laptop. And then I can execute a circuit on the simulator and look at the counts, so the output information. And so this is the ideal simulation with no noise. Basically, I've prepared a superposition state and I've measured all the qubits. So because it's an entangled state, if I measure 1 qubit in 0, that means all the qubits will be in 0. So there's only 2 outcomes. Either all the qubits were down or all the qubits were up with about 50% probability. So I expect this histogram to have 2 peaks roughly around a half each, like shown here. So now if I go back to what would happen on a real device, you'd never actually see this kind of thing because errors involved in when you're applying the gates and thermal properties due to the time of the simulation and also errors in the measurement. So the basic device model will take the properties of the backend and build a simplified noise model that includes single and 2-qubit local errors on all the gates in your circuit, which are based on the thermal properties of your qubits. So this is specified information about their coherence times called T1 and T2. And gate times, and it will also include the effects of readout errors, which are also given in the device parameters of the average readout errors. So if I go through and do that, so this is an example of building the noise model automatically. So there's a noise model class in Qiskit that uses to represent these general noise models. This piece here about gate times is because not all the devices report actual times for all the gates which you need for some of these thermal things. So I entered some in myself based on some specifications I tracked down online. And then I just call this function of basic device noise model with this set of gate times and properties, and it returns some object that describes what gates are the basis gates for my device. So even though you can write a circuit in terms of all sorts of gates, such as like X gates, Y gates, Toffoli gates, C0 gates, a device only implements a certain basis set that you have to compile your circuit into. So in this case, it's C0 gates and single qubit rotations. So when I want to do a simulation, now I have this noise model object. I also need the basis gates that I want to compile to most accurately mimic the device, which I can get from this noise model. And I also need the coupling map, which I got from the device itself. So the coupling map is that if I have a circuit that, for example, does a 2-qubit gate between arbitrary qubits, say like 0 and 4, but they're not physically connected on the device, that has to be remapped into several gates that connect those 2 qubits. So you want to model that as well if you're trying to mimic the most accurate simulation of your device. So now putting that all together, I can get the basis gates. Again, I use the local simulator. And now when I run the results, I'm including the noise model, coupling map, basis gates. And now if I look at the counts, I see something quite different. I see all these additional peaks due to errors in the device. So these are from the noise model, from errors in applying the gates and errors in the measurement. And typically for a very short circuit like I simulated here, these errors will probably be dominated by errors in the measurement. So you can see it looks very, this device, the Melbourne one, actually has quite high error rates for some of its operations. So here, these 2 large peaks in the middle for incorrect gates are, you can see that basically, if you look at the bit strings, it's this middle qubit that is flipped in one of the cases. So this kind of indicates that there's very high errors on this middle qubit in this simulation for some reason. So you can also run that on, as I mentioned, the online simulator behind the scenes is also using the same simulator framework. So you can also, if you don't have it on your laptop, you can do the same noisy simulations through our online IBMQ QASM simulator, and you get similar results. Of course, they're a little bit different because there's measurements involved, so there's statistical sampling that comes into play. And so if I then want to actually run this on the hardware to see what sort of errors I might get, I can execute the same circuit on the hardware. In this case, it doesn't look as bad, so the error model was actually overly pessimistic for this simulation. And so that's just to make a point that these basic device error models, you shouldn't think of being an exact representation of the errors on a device. They're a very simplified approximation based on these few number of parameters that are reported. And if you want to do a really, really accurate model of errors on a device, you actually have to do characterization of errors in your device, for example, using tools in Qiskit Ignis, and you can build your own noise model. But it's often a very good starting point to start looking at noisy simulations using something like this. So I'll just take a few moments then to jump over to this notebook. So this notebook is, if you care about building a noise model from scratch, this kind of describes how all these classes work and all the pieces that go into it. So you've got a lot of freedom in doing this, and the pieces are basically, as I mentioned, there's this noise model class that you use to represent the model, and then there's 2 error classes. So a quantum error, which describes these CPTP errors, so errors that happen after gates, and also an additional classical or readout error, that's the errors on the bit strings you observe after a measurement. And so for quantum errors, you can represent any arbitrary Krauss error by providing that list of matrices I mentioned earlier. But there's also many helper functions that exist in Qiskit to give you simplified error models that are often used in academic literature for studying classes of errors that have much less parameters. So you can consider, for example, a depolarizing error channel, which has a single parameter of a depolarizing strength, or a Pauli error, which has a probabilistic error of either doing an X or Y or a Z error on after your gate. And also, there's several other errors such as thermal relaxation errors, which are based on the thermal properties of the device from the extra heat and energy that's happening in there. And other kinds like amplitude damping errors, phase errors. So you can use these to build error models without having to manually write your own functions for all these common sort of canonical error types you might see if you look at the literature. And then these error objects themselves have a bunch of tools to help you build composite errors. So if I, for example, have 2 single qubit errors I want to combine into a 2 qubit error to apply after a 2 qubit gate, there's a tensor function that lets you do this automatically. If I want to compose 2 errors together to a single error object, for example, I say after a gate there's 1 error, then another error, then another error, I can combine them as well using these tools. And so some examples here is just of building a, say a bit flip or a phase flip error using this Pauli error class. I just specify the probability of an X error or no error, or a Z error or no error. And I can compose them together into one that now includes multiple kinds of errors. So in this case, it's either an X error, a Z error, or a Y error, which is an X and a Z error. There's also functions in QuizKit to deal with the mathematics of these error objects, so you can convert these into the error matrices if you want to look at them or study them, and back and forth to use with the simulator or for more algebraic kind of manipulations. So the other kind of errors I mentioned were readout errors. So for readout errors, these are a probabilistic error basically that you can apply to the classical bits, that if I perform the measurement and the measurement has some probability of being 0 or 1 based on the state of the system, then the error is given that the true measurement outcome was 0, with some probability I record it correctly as 0, and with some error probability I actually record it incorrectly as 1, and vice versa for the other one. So you can put in this probability matrix to represent one or multiple qubit readout errors. And again, like the other errors, you can compose and tensor product them together. Then once you have these error objects, you can add them to a noise model in several ways. So you can do a very simple model where I just say, anytime I do, for example, a Hadamard gate anywhere in the circuit, apply this error after it. So a sort of single parameter error model. You can also set different errors for different qubits, so that I have a different error, for example, if I do a Hadamard on qubit 0 to a Hadamard on qubit 1. And also, as I mentioned, so those are both examples of local errors, like I mentioned at the start. You can also consider non-local errors. So I can say that if I do a Hadamard on qubit 0, I have some error term that acts on qubit 0, 1, and 2, and I can specify errors that way. And there's methods to add all these errors to a quantum noise model class, and it will tell you about the noise model. And so this goes through some examples of that. And then, so at the end here is just a couple of examples of, again, building GHC circuits and adding noise models. So this now is a 4-qubit one instead of a 2-qubit one. So I could put in a basic bit flip error model, which is often it's a simple single parameter error model where with some probability there's a Pauli X error either before a measurement or after a gate. And I can build that noise model myself, say which gates it applies to, and execute it as I did before to see the effects of noise in my output distribution. I can consider thermal relaxation errors. So this is specifying gate times and thermal properties of qubits, and you can go through this for examples of adding errors and executing them. And you can build very, very highly customized error models this way, and there's more examples on the GitHub if you're interested in this. So that will about do it, I think. So that was a really quick crash talk in open quantum systems, simulating them on classical computers, and then how you can do this in QuizKit. So thank you.
Thank you very much, Chris. Any questions? We have this funny thing here, actually. 1 second.
Hello. Okay. Good. So let's say I finish all the tutorials.
Mm-hmm.
So what would you recommend me as a next step to go deeply?
Can you be a bit more specific
Yeah,
in
so,
what direction you'd like to go deeply?
Well, yeah, with artificial intelligence, machine learning, using QuizKit and quantum algorithms.
Yeah, so there's artificial intelligence was very recently some examples of that were added to the QuizKit Aqua library. So there's, if you haven't already seen them, there's 2 tutorials on it now, one on the quantum support vector machine and one on the quantum GAN. So you can go through them and have a look. After that, machine learning is actually a very recent area, so you have to start looking at the scientific literature for the most up-to-date research on the topic. And so we have various people at IBM that are doing research in this topic, and of course other research groups as well. It's very active. And then at least the kind of philosophy we have is that when we do research, and some researchers, for example, put out a new paper, is we try and incorporate that into our libraries so that then other people can start using them in, for for example, like the QGAN was a recent research paper by some IBMers at Zurich, and that was just added to Aqua about a month ago, I think.
Good.
Yep.
Any more questions? Yeah.
So which errors actually do dominate the physical devices you have?
So of course it depends on your architecture. For us with superconducting qubits, and when you're looking at the larger chips, like the 16, 20 qubit chip, so then one of the errors that dominates is what we call crosstalk errors. So crosstalk is basically a non-local error that happens between, so if you look at a picture of let me go to this picture. So you have your qubits on some chip, and they're connected by these squiggly lines, which are resonators. So that's what's used to do a 2-qubit gate to interact between qubits. But that connection also has the side effect that those qubits are interacting even when you don't want them to. So that interaction's ideally very suppressed, but it's still noticeable. So crosstalk errors seem to dominate these multi-qubit chips. So being able to study them and design better control pulses that can mitigate the effects of crosstalk is an important area of research that we're working on at the moment.
So you said that you have built a scalable simulator.
Mm-hmm.
So my question would be how scalable it really is. So because you told that it scales with on servers. So the question is how many servers can you use?
Yeah, so at the moment, this is something we're still developing, and my colleague at the back of the room, I could throw him under the bus to answer this, but basically at the moment it's really for a single node server deployment.
Mm-hmm.
The problem, you can start looking at doing multi-node server deployments as well, but you have a challenge that now you're, for example, distributing the quantum state across nodes, and the problem is that unless you have very specific types of circuits and carefully engineer the order you apply the gates, doing even applying a gate to a single qubit has to update the entire state vector, so that involves a lot of this internode communication, which will become a huge bottleneck. So for that kind of scaling, you have to start looking at more specialized simulation techniques with maybe tensor network contractions or something. So this is also an area we're exploring.
Yeah.
Any more questions about what to do with Qiskit, with the air, how to do it, how to log in? Right, then thanks very much, Chris, for this nice talk.
Thank you.
And the next talk is from Fred. Do you want a break? Oh. You have a break. All right, then we're going to do a 2-minute break.
Just as a proof of concept, what I have done to practice to do the exercises, you need 60 bits. Yeah, I didn't get the trouble. I'm not sure it's supports our use. Yes, hyperbots, or maybe they have some packages. I don't know. I hope it should. There should be one of the motivations for using Python and using C++ for which can invest because they are usually most of the time at early stage they are interested with and not very Windows friendly. At least Windows for both worlds. There's not much going on with Linux, so no one can fix it, right?
Yeah, I don't have good desktop.
So most of the time I don't say Würfel nehmen oder?
Ja, mit dem Würfel, das ist schon heftig.
Shall we resume in 1 minute?
Der ist hier.
Okay. Dankeschön.
All right. Let's start with the second talk of the day. It's going to be much less equations. What I'm basically going to talk about is what we do in the lab. I'm working in Heidelberg University as a researcher on quantum systems. And the goal we have is basically trying to push the limits of theory and experiments of interesting systems that we could have. Yeah? And so my assumption was that people don't have too much of a background on quantum physics, and I want to give you a few little ideas of how you should think about it. So the first person a lot of people associate with quantum physics is typically Mr. Heisenberg. And so he actually knew very well how to use quantum physics and how to earn a lot of money with it. And a second famous physicist, not Heisenberg, but Schrödinger. And I personally like Schrödinger a bit more because of the picture he used to explain quantum physics. And I actually think that most of the things that you understand most of the experiments that are done, you can understand them quite nicely. So there are two things. You have the cat in the box, and it's dead and alive. So this is a very general principle you have in quantum physics. You can be in the superposition of any accessible state, and you have to let the system accept this for the moment. However, this first rule only works as long as you do not look. So once you open the box, the cat is either dead or alive. Okay? And if you follow these two basic rules, then you basically can explain the systems quite well experimentally. And also, like, the math formalism behind it is very much implementing this idea here. Okay? So why is this idea making it so hard to do the calculations and so on? Well, here I took a picture from a group in Harvard, and each of these green little dots is one atom that you put on an array. Okay? So, and in each of these dots, you can do these Schrödinger cats. So each of them can be either dead or alive. And only if you already take two, well, in the same moment, you can have them both being dead, both being alive, and all this cross-term, right? And now if you have the 51 of them, well, you can access basically these petaplots. So simulating this on a classic computer is a nightmare. Doing this in the lab is very hard, but you only have 51 atoms here. So if you control the 51 atoms, it's a very nice system, and it's not particularly hard. So can we scale this to something where we really push the theories to its limits? And yes, this is another group in Harvard, where you can see basically very nice experiments. These are all single atoms on a big lattice. And what they can do is they can hop through the system and talk to each other and do all kinds of quantum physics. Completely impossible to calculate this system, and even for a quantum computer to simulate this, it would be years and years to do this. So if you're interested in systems like hopping on a lattice, which you have a lot in material sciences, where you have electrons which are hopping through a lattice, then going and building a system like this might be the right way to go, to really push and understand new physics about the quantum systems. Okay? And that's basically the branch of research we are working in, or I'm working in. So atoms are not the only thing that you can do there. There are plenty of platforms people can use. So the ions and the superconductors are the typical tool of choice for experiments to build quantum computers, where you have 5 qubits, 10 qubits, and things like that. The neutral atoms, in this little fireball here, you have something like 1 billion of the atoms. Okay? So the advantage of this platform is that the systems are typically much, much bigger, but you give up the precise control over the individual constituents. And that's the big thing. Other tools are, of course, light, photons. People mostly know electronics. This is the Microsoft people here. And diamonds, for example. If you have little color centers in diamonds, little impurities, you can use them to measure magnetic fields insanely well. These are some of the best magnetic field sensors that exist there. So each of these different tools has very different kinds of applications and where they are used. You always have quantum physics, but you might want to use very different things with them. Quantum computing is by no means the only thing. And this is just to show you what in our lab is happening. This is here, basically we fill up a room which is 30 square meters with all kind of electronics. In here you have an oven, there you have a vacuum chamber, and then in here this is the little picture I showed you. Okay? And then you have here plenty of light to control the atoms. To run a machine like this, it takes 3 or 4 graduate students. And years of work. Building it up is 2 to 3 years each time. Just for showing you the complexity of we don't advance very fast because these experiments are just from an engineering side of point of view extremely hard to do. They are basically at the limit of small experiments. So if you have this, then you can run different applications for them depending on what you want to do. The first thing is if you have photons, you can use quantum physics to do very secure communication. You can exchange photons and basically use them to be really sure that no one is listening. Here China is really pushing the limits by far. They recently implemented a little node where through satellites they could have quantum secured communication from Vienna to Beijing. Okay? So this is really now state of the art. You can buy these things increasingly. Then this quantum sensing is another very well established platform where you can build the best magnetic field sensors that you might want to use for industry. They are all based on ideas of quantum physics, so also widely used in application. The quantum computing platform is the most fascinating one maybe because you might build new kinds of computers, but also by far the hardest. Because you have to not only control a single ion, which you might see here, but hundreds and thousands and millions. Okay? And then the fourth option is actually the option which I'm working on, and that's called quantum simulation. You take your atoms, you put them into the extremely right constraints that you want to investigate, and you let physics do the solution of your problem. If quantum physics is what you want to solve, then maybe the quantum particles are the right guys to do this, not a classical computer. And that's the idea behind this. So I want to talk a tiny bit more about the quantum computation and then the quantum simulation, because this one is really, by now, you can buy it, basically. Yeah? So what's the idea here? Well, let's say that Chris and Niklas didn't want to just talk about this meeting here, but they had some very, very fancy ideas, and they absolutely want to be sure that no one is listening. But obviously, you have evil guys like Mr. Heidelberg who really wants to know how to do better quantum physics. How are you sure that he's not eavesdropping? Well, everyone here involved knows quantum physics, so they'll go to the company called ID Quantic, and they will give them these kinds of pairs. Out of this box comes a pair of photons, and each of these photons is in the superposition of being dead and alive. They prepare this, and then they send this to Chris and Niklas at the same time. And what they know is, exchanging these little cats in the background, is that Chris and Niklas should always see a cat that is alive or that is dead. If one sees like something like this, and the other one sees this, they know something might be wrong. Okay? So now what happens if Mr. Heidelberg tries to call in? He is getting the information, he sees something like this, But now Chris and Nicholas will not get the same information anymore. So the probability of having exactly the same kind of information will break down, and they know that someone is eavesdropping. They don't know who it is, but they can stop the call at this point and try to see it better live. Okay. So this is this encryption keys, which you can basically use by now. The second thing that I wanted to talk about is really my line of research. And here, the idea is to use our atoms to simulate things which are hard in other environments. So given that I came in through here in Frankfurt, and the guys from Just Quantum are working a lot on this financial sector, I think a good idea might be the stock prices here in Frankfurt. So what you want to do, and what's very hard and also very good for business, is try to predict where at the stock price will go, whatever price. You can solve this problem, you're a billionaire, right? So this seems like a good option. So you look at this stock price, and what you see is, well, what are the daily returns? And this seems to look like a bit random. Is there more to it? Is it just randomness, or is there more to it? And then as a physicist, I start to wonder, how can I explain these observations? So if I just take this, I personally see something like an atom that is hitting little obstacles time by time and creates a random walk like this. So these classical random walks are widely used to understand this model of efficient walk markets in finance. But now, this is a classical model. We have quantum physics available, and the idea is there more to this story. And in quantum physics, you should remember there's not just one way of doing this. If there are several possibilities to take a path or to do something, you have to all take them into account. So what we would do classically, the picture that I showed you is, I'm starting here, and then I start moving out, hitting some walls, and going all over the place, right? This is what we would call diffusion or Brownian motion or efficient markets, depending on who you are and what you like. But then there are some very special passes that you can take. Imagine you start here, and it happens that you come back to the origin. Well, this is one way of doing this, but there's also another way of doing this, exactly the opposite way around. And you can't distinguish them. So what will happen basically due to quantum mechanics is that the likelihood of coming back to the origin is increased, and the particle basically wants to stay at the origin. And this we can now implement actually in the lab. So this is already by some time ago now, is you take this idea, and now this is this rigorous potential that you see, basically where the atoms scatter. And all they are allowed is move back and forth the line. And you release them in this order, how we call this, or these rigorosities, here at the beginning, and then you just let them expand the line along. And they expand, and then they expand for like half a second or something like this, and then they just stop. They could continue, there's nothing hindering them, except the quantum mechanics just makes them stop, and they sit there and they won't move again. Yeah? So basically this classical idea that we would have of oscillating around and we can get back and further and further away is completely breaking down here due to these effects of quantum mechanics. So the question then is, so this doesn't sound at all like the idea we have of the financial markets where we have this Brownian motion and we can move arbitrarily. So then there are systems where you can have both coins. So you again, don't let the atoms just start out at the center and let them move on a line, but you let them move anywhere in space. And the idea is now that these closed loops that I was talking about at the beginning, on a line, whenever you want to go back, you have closed this loop, right? If you want to do a random walk in this building and you don't know where you go, the probability of coming back where you started is very, very, very unlikely. So these effects that I've been describing actually depend a lot on, we call it dimensionality. Are you allowed to move on a line, in flatland, or on a building like this? And in a building like this, you can have the situation that some of the atoms are moving exactly like we would explain it by classical physics, and on the other hand, exactly like we would explain it by quantum physics. Okay? And the question why we started talking actually with just quantum a lot is, can we have similar observations in financial markets? Problems that look in some situations like the classical diffusion that we have, but in some situations these kind of problems are breaking, these kinds of ideas are breaking down. Yeah? And so we really want to build kind of quantum simulator for these kinds of markets, and we have to understand which kind of equations are following the markets, which kind of equations are following the atoms, and can we bring them together. And then really push the theory behind what's known. And so I wanted to keep it short and have time for questions. So this brings me already to the end of my talk. And now I'm happy to discuss things about the beer and that Mr. Heisenberg also did it after Heidelberg. Thank you very much. Questions?
Yeah, thanks first, Fred, for this interesting talk. Are there any questions in the room? Yeah. Yes.
Thanks for the nice talk. Just want to ask, when quantum computing, you hear a lot about commercialization efforts by Google, IBM, etc. What's the status neutral atom commercialization? What's quantum simulation, neutral atom commercialization?
So the first pictures that I showed you with these 51 little qubits there, there are now companies in Paris which start on this and so on. For the larger systems which we work with, the big problem is actually translating what we do in the lab into the real world applications. The nice thing about the qubits is that you have this simple language of the circuits, so you can talk with people outside of physics and they rather rapidly grasp it. For the atoms, it's a much harder. You have to be basically a quantum physicist to understand what's going on. And so there's no commercialization efforts going on in this line of direction. If you have, I mean, it's fundamental research for the moment. Just because you have to be able to talk about the model that you want to solve in the quantum language and also in the financial market language. And this is the very hard problem there. But for the moment, I'm not aware of any commercial.
Okay. Can you say a little bit more about the diffusion, localization, and dimensionality?
Yes.
How that's linked, and as a non-quantum physicist, I'm just interested in how that works.
Yes. So, I mean, this localization and diffusion thing, it's really an interference phenomenon. Okay. And I mean, this picture that I gave, I mean, let me go back to the picture that I showed you. This picture here, it works very well for understanding basically everything. The big point is that you have these indistinguishable passes. So the wave functions are, to get the probability of coming back, you basically have to square the amplitudes here, which gives you an increased likelihood of return. And in one dimensions, or like when you only can go back and forth, this effect is just completely killing any diffusion. If you go through the calculations, the distances over which this localization is happening, when you have basically no transport anymore, depends on how strong these scattering events are. But you will, in one dimensions, a very strong theorist statement could be, in one dimensions, any disorder will lead to localization. That's kind of the idea there. In 3 dimensions, it's much more interesting. Basically, the idea here is that you need to have the very strong disorder to have this localizations effect to become an important role. So you can have a quantum phase transition between passes of low-lying energies where you're localized and high energies where you're not localized. And the pictures that I showed you were basically having both components within the same idea. And the reason why they are so much smaller is, well, in 3 dimensions, the likelihood of having such a closed loop is just much smaller than in 1 dimension. In a random pass in 1 dimension, the probability of coming back to the origin is 1. 2 dimensions, it's for infinitely long times. In 2 dimensions, you have to make much longer, but I mean, you will always come back anyway. And in 3 dimensions, you don't come back, except for rare events. I mean, the probability is much smaller than 1. This is basically the idea there for these. Did this answer the question?
Yeah, it raised a whole bunch of other questions.
Yes.
Anyway.
Yes.
So another one.
Here we go.
Okay, so how reliable I'm totally 100% sure is that in the picture you sent about the communication between Chris and me is totally sure, because couldn't be the case that the communication could be hacked and the Heisenberg could replace the he knows the result. I'm asking this because recently, 2 weeks ago, like, there was a big announcement about, it seems like the cat, it seems like there are some small conditions that really is not so, so you can start to see when you start the entanglement, right?
Yes.
So this is really, it's really 100% sure for sure, or maybe there is something that is still not discovered.
The theory is 100% sure for the moment. Okay, so let's say it this way. It's been now, this is I could go on for a long talk, or the short version is the theory is 100% sure. The loopholes are basically coming in for the experimental realizations, or the lab realizations. So if Niklas and Chris could both detect with 100% fidelity, and they would never make any errors in the detection and the preparation, then it's good, right? These loopholes that people talk about come in the situation, well, maybe the cat that is prepared here is not always and perfectly a cat. So you have to put in some thresholds of reliability. The same thing is here. Maybe Chris is detecting that the cat was alive, but it was actually dead. Another error that you always have in one. So if someone is very smart and he can exploit these loopholes, experimental loopholes, then you have a problem. But that's the basic idea there. To be like, this is typically how the story goes. Someone says, well, the experiment is not perfect. How can I exploit this imperfection in the experiment? This is 99% of all papers there. But the idea is very much there, and it's working very reliably already. This is.
Thank you. So I have 2 questions. One curiosity. So what is the bandwidth that can be commercialized with this quantum? Well, how much you can call?
So it's in the kilohertz bandwidth. So what you do with this is every milliseconds or things like this, you send out these little cats and you look and you verify that your communication is you distribute the keys basically. You test that it's reliable. You are not sending your video stream through these cat systems. This is yes.
I see. And then I have another question regarding the Apple example. So I would say usually when you think random motion or something like that,
yes.
The example is always like the original example is the particles of water, no?
Yes.
So there is this random heat, and, and in the market this is people that decide to buy and sell.
Yes.
While for quantum, there is an intrinsic randomness inside the system that you are analyzing.
Yes.
So why do you think that stock options, stock equities or whatever it is, have this intrinsic quantumness that is similar to a quantum system?
So it really depends on your interpretation of the stock market, how it works, right? And we do not know, but we might have, these kicks here could be just some kind of an event. And so you have to sum up of the different kinds of possible ways this market might go. So the way I see it typically by now, the idea, and we have to go through the equations and everything, right? But a possible thing is, what happens if the potential buyer might buy, but there's no market for it? Yes. What happens now? Well, he could buy, but he also could not buy. The event didn't happen, so you didn't measure it. This is exactly what happens in quantum physics, right? It could happen, but it did not happen. This is what these probabilistic events are exactly for what the mathematical framework is set up for. The other thing is, these equations here are by no ways specific to this whole entanglement discussions. Whenever you have waves and you can have coherence phenomena and collective phenomena, these equations still hold. So it is very much on the phenomenological level also where you, I mean, I don't know the underlying equations for the stock markets, right? So I have to speculate, could they apply? But if I look at the stock markets and I can see certain observations there, they sound a lot like what I know from politics. That's basically right now the statement. And now the question is how to bring them together here. Yeah. This and this.
Quantum physics after or before the measurement? So this is
yes.
Because after the measurement is just the statistics.
Let's discuss this after. This is, I mean, let's be clear, this is speculative, but I think it's not completely ridiculous.
No, just
yeah, no, but it's
so the assumption is that I mean each buy and sell on a given stock is always, it's a rational decision and there's a cause behind it.
This is the assumption here, right?
Yeah, no, but if you look at the market, there's somebody somewhere says buy, sell, or some computer program says buy, sell. So it's a causal, each of those.
Yeah, here
changes.
you bought, here you sold. I mean, you know.
And there's a causality behind that with a whole bunch of effects. Yeah.
Yes.
Completely independent or dependent on Apple's. They just made an announcement, or there was a storm in Kuala Lumpur, or I don't know, whatever. You know? So the assumption is that a sufficiently large number of external causes, the observed behavior is random. Looks random.
I mean, yes. I cannot make a clear prediction. I mean, this is a very, I think.
Yeah, I mean,
yes.
If you look at.
I mean, these are random walks. I mean, if you could, that's the assumption.
Yeah. Okay.
I mean, we can. Yeah, I'm happy to discuss this in detail. But this is basically the randomness. Assuming that the randomness to the financial market is kind of intrinsic. Doesn't seem like a stretch to me. But I mean, this is maybe just me.
No, I was just thinking about people using a gauge series to model financial markets as well. So that kind of fits with that, sort of.
Yes. I mean, one thing. Exactly this kind of question. I mean, you know, the lab. Most of the time, I'm really focusing on getting these experiments running. And the financial markets are exactly the kind of point why we keep discussing with them, because I mean, you can come up with all kinds of theories, but basically you want to make a prediction, right? I mean, this is the big thing, and so you have to understand what kind of financial markets this could apply to nicely.
Yeah.
Sorry.
Yeah, it's not a question, it's more like a comment. So the general behavior you observe, like the random walk of a stock price or something, is actually not time reversible. So the general process over a long period of time, you won't be able to describe a quantum process, but that doesn't mean it's not a useful thing.
So any more questions, or shall we switch over to beer and the rest of the food? All right. Oh yeah. We have one more slide to show. Actually, I'm wondering if it should have been in the beginning, actually. Yeah, here it is. One last announcement for the evening. We are running a hackathon in September, 21st of September, in the Institute für Neue Medien. It's a pretty cool and creative location in the eastern part, in the haven, Osthafen in Frankfurt. And it will be like a 24-hour challenge included. So we're going to work on different challenges in building quantum computing algorithms. We're going to propose them. You can bring your own. We are very happy if many people are joining and applying. Just go to our website, www.just-quantum.de/quantum hacking. Fill out a short form because we need to know a little bit what are your skills and pre-knowledge, so we mix up a good team from like people knowing the economic sides, the software side, the coding side, and the quantum mechanics side. So please join us and like us on Facebook and Twitter. And yeah, let's have a nice evening. Thank you very much for coming, and see you soon.
Thanks.